Okay, good afternoon, everyone. I hope you are doing all right. Today, in our neighborhood, our internet service provider is doing some sort of network upgrade, and because of that, they're flipping the switch of the internet. Looks like it comes and goes. Okay, it was off until 2 o'clock, so that's why I just joined at 2 o'clock. So hopefully, it stays on. If it goes away, then yeah, of course, I will be offline. And usually I don't know what it's gonna do. Okay. So if I vanish, that means my internet is gone. Okay. Hopefully it comes back soon, even if it goes. Okay. So we're gonna start talking about relativity. So it's like a relative velocity, but when the velocity goes in very high limit, what happens. So those kind of things we're going to be talking about in this class. So let's start by just looking at the relative velocity thing that, even the common sense uh, gives us the answer. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly B, and that is correct answer. So beer itself is already moving 4 meters per second and biker is 5 meters per second. So their difference is just 1 meter per second. Okay. So it's like a driving car. When someone else is driving 40 miles per hour and you are also driving 40 miles per hour, and then what happens? The relative speed between you two gonna be zero because both of you gonna be on side by side all the time. Okay. So same idea. So that's called relative velocity. But if someone is, coming this way, and another one is coming that way, then they're gonna approach faster. So their relative velocity gonna be higher. So we add them for that, right? So yes, so B is correct answer. Okay, I'm back. So now let's see how it goes. I don't know. Okay, hopefully it works out. This is kind of annoying. So we are talking about relative velocity. So motion is relative. That's what this Galilean theory of relativity says. So what it means is the speed or the velocity you measure depends on uh, what whether you are moving or not. Okay, that's what it says. And there is a term called inertial frame. So what that means is that if the object is not accelerating, means moving with constant velocity, means the velocity is not increasing or decreasing, and then that means we call that the inertial frame. That follows the laws of inertia. Another way, it follows the laws of motion. Okay, that's all it means. So when we have this kind of situation, then we can do the velocity transformation simply by writing something like this, right? So total velocity relative to the ground. So here, ground, this observer is at the ground. And that frame of reference for this, we are saying, okay, the coordinate system for this, we are saying yes. Okay, so it's just a coordinate system, but fancy name is inertial frame. Okay, and similarly there is another inertial frame, primed frame, that is moving relative to the ground. Okay, so that's what this diagram is showing you. So in that case, if you want to find the velocity from this frame of reference, then you can do this kind of addition. So u prime here is the motion of the object that's already, that's motion of the object is in moving frame already, right? So it's like saying there is a train or big bus, and the person is walking inside the bus or train, and the train itself is also moving. Okay, so this person is moving in this moving frame already. Okay, so it is the motion in primed frame. That's what it means. And v is the relative velocity between the observer at this frame versus this s prime frame, relative velocity between them, right? So when this person is looking at this train is moving 6 meters per second. And if there is another person inside the train and looking at this person, then this person here is moving at 1 meter per second. But for the observer in the ground, what happens? Train is already moving 6 meters per second, and this person is moving 1 meter per second on top of that train. So the total becomes 7 meters per second. So that's how you add them. Okay. Oh, u prime plus v. Maybe I should have written 1 and then plus 6. 6 is v, and u prime is 1. It's the same thing result, but I think I should have written 1 plus 6 here. Okay. And if so, that means it becomes 7 meter per second. And if you like, you can solve this velocity with respect to this frame. And in that case, what happens? Portion in this frame, I'm gonna see just 1 meter per second. So u is 7 we just found, and b is already 6. So 7 minus 6 becomes that, okay? So basically, this can be just written in terms of intuition, and I have written few other examples in my note as well, okay? So in that case, what happens is that we are not doubting that the portion here in this S frame means the frame that's not moving, okay? So, and then portion or the observer in this frame, they can measure exactly the same time and the same length and so on. So that's what this is assuming, okay? And that makes sense, and usually that's what happens, okay? So this in Galilean relativity, time and space are absolute, the same for everyone, okay? So if you are, let's say you have a watch on here and you are in this train, and let's say this watch is bigger, that portion outside, or let's say there is a clock rather than watch. So portion outside here can also see that watch. So in that case, what it means is the time shown by this watch to this portion here and this portion, they are same. Okay, there is no difference. And that's the case for the speed, that matters for us in our daily life. But when the speed goes really high towards the speed of light, then that changes. And that's where the Einstein's theory of relativity comes in. Okay. And it's not just the time, even the train or the length of the train, or let's say length of the clock, you know, for this portion here, if this is this big, for this portion here outside, that may seem smaller than that. And that change takes place only in the direction of motion, okay, in terms of length. So we'll talk about that more, but this is what was assumed, right? And we were comfortable about that. And then what caused the problem? What prompted Einstein to modify that? So that's what we're going to be talking. And what's the consequence of that? And how much time changes and so on. So that's what we are planning to talk in this class. Okay. So now here is another question for you, not related to what we just talked about, but based on what you think, right? So first I'm letting you think about it and then gonna talk about it. So 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So mostly up and down and comes back to your hand, and that is correct. Okay, and that is what I have drawn here. Okay, so now what do you see here is that whether you are standing here on the ground, assuming that ground is not moving, let's say, and if it's not moving, we have this S coordinate system. And for the moving card here, it is S prime. Okay. So now When you just looking at the ball you are throwing straight up, that just comes to your hand. And if you are inside the train, as long as the speed is constant, what happens? It comes back to your hand, even when you are standing inside a moving car or truck or something like that, right? So it comes back. So that means whatever experiment you do related to gravity, laws of motion, and so on, inside this versus over here, they're going to be same. Okay. So here, if you look from outside though, the path, see the car was here when this ball was thrown. Now car is here and ball is returning to the hand of this person. So if you are looking at the ball thrown over there inside the moving car, its trajectory is different because this car is moving. So this ball was also is also moving or was also moving when it was thrown, when it was released from hand, although it was thrown up. See, even when it is not thrown up, what happens? If you are holding a ball and you are in the car, then the ball, you and car all moving with the same velocity. And for the person outside, what happens? Again, you, car, and the ball is moving with the same velocity. So when you throw this ball up from the car, what happens? It has this velocity and you throw with some velocity, let's say b prime. So what happens in that case? So these two velocities being, vectors, we can say, okay, they get added. So it's like as if you threw something like this. So the ball starts something like that, like a projectile motion we talked about. Okay. So that's what happens. But the thing is, as long as this card is moving with the same, constant velocity, or as long as this frame is inertial frame, what happens? It comes back to the hand. So for the person over here, it still looks like, okay, you know, the ball went straight up and came down because ball and the person, they are moving with the same velocity. So relative velocity between person and the ball is 0. So it's like not moving. It's like you know, if you are at a restaurant or home, you can dine just fine, right? You don't have to worry about spilling the drink and so on. And so is the case when you are in the plane, for example, flying. Once there is no turbulence, means it's not accelerating, it may be moving like 600 miles per hour. But what happens? You can eat, drink, do whatever you like as if you were on the earth. Bit congested, but perfect. Okay, unless there is turbulence, you don't even feel like it's moving. So moving with constant velocity is like not moving. It's a relative thingy. That's it. Okay. So that's why the laws of motions are same for these inertial frames. Okay. So now, if you are in this car and car is moving with velocity v, let's put a number. Let's say 60 miles per hour. And let's say you are really good thrower of the ball. Okay. You had a baseball experience or something like that, and you can throw really fast in the same direction. And then what happens? Just like we saw in the previous case, if this person from the ground is watching that, and if this ball is 6, let's say, miles per hour, oh, I think these baseball player, they can throw really fast. Let's say 60 miles per hour, 80 miles per hour, I think, and they can throw. But let's say 60 miles per hour. Then you see the ball launches or goes with 120 miles per hour. The ball was already moving 60 miles per hour before it was thrown. Now it is thrown with 60 miles per hour. So total becomes 120 miles per hour. Okay. So nothing, that's surprising here. It is expected. And that is basically Galilean. But now let's suppose we have something like this. So there is a bike, but this bike is, like let's say super bike. Okay. It can go really fast. How fast? Oh, 95% the speed of light. How much is the speed of light? That much. And what is that number? 300,000 kilometer per second. So really fast. Okay. So this light within let's see, within 3 seconds or so, light can reach from Earth to the moon. So that's how fast. Oh, 300,000. So within a second or so, this light can reach to the moon, or light from the moon arrives to the Earth within a second. So forget about light going from here to where you are. Okay. So it's moving really fast. And this happens to be, let's suppose this bike can move 0.95 times c being the speed of light. So 95% the speed of light, right? The bike is already moving at that speed. And then there is this flashlight connected to the bike. So that means when you turn on the light, what happens? Light from this flashlight, it starts with the speed c. So it's like saying, okay, we had 60 miles per hour. So that is like a 95.95 c train, right? And then you throw a ball with 60 miles per hour. So if you are shining a light, that means the light starts with the speed of c, right? So that's what I'm trying to, give you the impression that this thing is moving really fast. So that's what I'm assuming that. So it is a super bike. Ordinary bikes cannot move that fast. And you have this source of light that, lights up and emits the light. And light always, like light also starts moving with the speed c. Okay. So when we talked about electromagnetic wave, we saw this equation, and this equation tells us that the speed of light in vacuum is this much because this is constant, and when you plug in, and this equation was derived by Maxwell, okay? So that's how we know the speed of light is c, okay? So now what do you think with respect to the ground? So for example, if you are standing on the ground over here, and then measuring the speed of this light, what would you see? So that's what this question is. So let's go ahead and poll on this. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. So let's see what we got. So we got all of them. So based on what we talked, about that cart thingy, it should be this 1.95 c, right? Because something was moving 9.95 c, and then now it starts with 1 c, so it should be 1.95 c. So that's what one would expect, but turns out that does not happen. Rather, what happens? If you measure the speed, you get just c. So that means light is not following the Galilean relativity, right? So for example, if our bike is moving 60 miles per hour, and if you throw a ball, let's say 10 miles per hour, then the observer over here gonna measure the speed of this ball as 70 miles per hour, 60 plus 10. It was already moving 60, and then now on top of that you throw with 10, means it starts with 70, right? So that's what we expect. So based on that, this is what we would expect. But when you do careful experiment in this kind of situation, what happens is you still get C. So 60 plus 10 is 70. That mathematics everyone knows, right? Every kid knows. And 0.95 C plus 1 C, which is 1.9 C, that mathematics everyone knows, right? But what we don't know is how come 0.95 C and 1.95 C is still a C. That mathematics no one knows. At least no one knew until Einstein came up with the new formula for adding velocity and so on. Okay, so until Einstein recognized this problem. Okay, so what was the dilemma for the Einstein? So just like we said, the speed of light. So they did this different kind of experiment. Okay, I'm not going to talk about these experiments here. If you are interested in history of development of science, feel free to search for these experiment and then read about them. But what they try to do in all these experiment, these were the experiment. Of course, this is theory we already talked about. Okay, second one was theory, and theory said the speed of light is constant, and they try to measure, like they set up an experiment that can measure the speed of light, but they set up that device in a motion. So device was moving while it was trying to measure the speed of light. Okay. So for example, I think in case of Michelson-Morley experiment, he had to wait for like 6 months. For example, when Earth goes around the Earth, we are sitting on the Earth, but the light is coming from the sun. So if you are trying to get light from the sun and measure the speed of that light, when in this part of the orbit, the Earth is moving something like this. And what's the speed of the Earth? Around 30 kilometer per second. So it's moving really fast. Okay, 30 kilometer in 1 second. So it's like 20 kilometer, sorry, 20 miles, nearly 20 miles in 1 second. 20 miles gone. Snap, 20 miles gone. So that's how fast the Earth is moving relative to sun. Okay, so when you are measuring the speed, see, this is when it is going one way versus another way, it is moving in opposite direction. So they should get the different speed of the light, but they did not. What happens? They keep getting the same value as suggested by this equation. So there was this crisis. Okay, why light is not slowing down, not moving faster? appears to move faster or slower relative to another object, right? So this was big problem, okay? So that's what I'm saying here. So it is for all observers, no matter how fast they are moving. Even when they are moving very close to the speed of light, it's the same, okay? And that's when the Einstein came up with this idea. So he made, like it was already known, he just postulated and explained why, okay? So this is also called, theory of relativity, these two statements. So that means physics is same in all inertial frame of reference. Physics does not change. Just like we had for the, you do the experiment inside a flying plane, as long as there is no turbulence or slowing down, right? Over there versus in a room, you get the same result. So physics is same in all inertial frame. Inertial frame means moving with constant velocity, not accelerating, okay? So that's that. Another thing he used was this already known fact that, from the Maxwell equation and indicated by the experiment, and said, okay, speed of light is same no matter what. It changes when it goes from one medium to another medium, but within a medium, it's a constant. We learn light changes the speed, right? That's why the refraction happens. We learn that. But as long as it is in one medium, the speed is fixed. And this value is speed of light in vacuum or in air. So that's what was added on this theory of relativity, which was the Galilean theory of relativity. Okay. So now what happened is that when you say, okay, light speed does not change, then you have to make changes on the thing, like the time portion measures in one frame of reference versus time measured by another person in another frame of reference is going to be different. It's not same anymore. Just like I said a little earlier, if there is a clock over there and there is a person, so there is, let's say, a clock here, okay, and there is a person over here, and looking at this, and of course, this thing is moving, and there is another person outside that train, let's say, who is not moving on the ground. What happens? We said, okay, the time should be same. Time we see gonna be same. That's what we see, okay? Now Einstein says, nope, this time going to be different for the observer at different frame of reference. Time not going to be same. Similarly, if you are measuring the length of this clock or width of the clock, let's say, then it's going to be different. Okay. And then velocity addition formula also has to be modified. So that was the consequence of those two postulates, especially the speed of light being constant. Okay, so it turns out that time gets dilated means it appears longer for the observer who is not in that frame of reference where the clock is moving, and length becomes smaller, seems smaller. Okay, and now velocity, to add the velocity, we have to have separate formula. Okay, so that's what that is. So how Einstein? So Einstein did not do experiment. He is not experimental physicist. He is theoretical physicist. But he thought about the experiment. If I were to set up this kind of experiment, then this is the result I expect. So that those are called thought experiment. I think they call Gedanken experiment in German language. Okay, so let's just stick with thought experiment. So how can the speed of light always be the same for everyone, no matter how fast they are moving? Unlike the case of, you know, in our everyday life, what happens? Ball throw from the moving object. The ball start with higher speed, it goes farther, right? But for the light, that's not the case. Okay. So for that, so that's for that reason, what happened is he had to modify that, right? So they have to disagree on the time versus the space. So basically, this slide is also kind of talking with what I just said. But here, let's think about this one here. So in this setup, what do you see? There is this train, bit longer train car, let's say, and there is this person and doing experiment, and then there is a flash of light that starts moving in both direction, and this person, see the speed of light is c, and the distance, since this person is standing right at the middle, the distance is same on both side. Distance of these walls on both side, they are same. So distance is same, speed is same. So speed same, distance same. For this observer who is moving, let's say at s prime frame, and this person over here is in frame s, right? So for this person, what happens? Both of these light pulse reaches at the same time to two ends, right? Now, what do you think this person gonna see, right? So that's what I'm asking. Let's say I'm standing on the ground. What do I see? So this is me. Okay, so what do you think? 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what did we get. So reaches both detector same time, and front detector first, and back detector first. So we got all these three responses, slightly more for B, and turns out that is correct. And we can explain that. Okay, we can explain that. So that's what this is about. Okay, so what happens? So this thing is moving, and when light pulse is started here, for this person, what happens? The train, this end of the train arrived closer from where the light started, so this distance, but this front portion of this car is already there. So that means the light pulse on this side has to move, let's say d prime, and this is d. So d prime is larger than d. So that means for this person gonna see, okay, this light arrives faster, right? On the back arrives faster. Is that what that was? Light reaches front detector first. Oh, actually, it should be back detector first. Okay, that wasn't the good choice. Okay, so it should reach back detector first. Okay, my bad. I carried away by the democracy, more vote. Okay, so So a smaller distance. So that's why what happens is this person sees, this one arrives first. So what that means? So for this observer who is already on this frame of reference that is moving, these two are arriving simultaneously. But for the another observer which in the different frame of reference, they are not simultaneous. So they even whatever you say, okay, you may say, okay, this happened now. I might say, no, it did not happen. It's not happening now, but now it's happening a little later, or it happened already earlier. Okay, so you and I, if we are in two different frame of reference, means if I or you, we are moving with constant velocity with respect to each other, then in that case, what happens? One person may think, okay, it happened now, but another person may think it happened slightly different time, earlier or later, same event. So even the event, they are not simultaneous. There is relative. It depends on who is observing. So that's what this experiment is trying to say. So there is challenge. Okay, time is not same for same all observer. Did you notice that? Time is not same for all observer. For one observer that is moving or in one frame of reference versus another observer, the time is not same. It's not happening at the same time. So that means what time we see versus what another person sees at different frame of reference, they are not same. So that's what this thought experiment is telling us. Okay, and it's not just the thought experiment. You should be able to actually design this experiment. So let's suppose there is a detector at the end of the wall, then you should be able to see, like let's say once the light arrives, let's say it's flare up some sort of light, right? So you should be able to tell that, tell when did that happen. So person who is in the train gonna see it happen at the same time, but the person outside gonna see it happen first here and then later over there, because detector is moving away from the light. So if you are chasing a person, let's say there is a person who is coming towards you and you are running towards that person, you arrive early, you meet earlier. But if another person that you are trying to get is also moving in the same direction you are moving, it's going to take longer to get you, or may never catch, depending on what the speed is, right? So here that tells us, okay, time observed by the same observer two different observer may not be the same. Okay, so that is kind of bit breakthrough in terms of, okay, what we say, okay, this happened now, or whatever we think this is now may not be now for another person. Okay, so for example, if I were to formulate right in terms of distance times and the speed, so speed of light is c, I'm saying. So let's say, for one observer, for this observer here, what happened? This distance is just delta x, and the time it took is, let's say, delta t. For this observer, what happened? This distance over here is now not delta x, but rather this is delta x prime. Okay, and so that's why the time is also different, but the speed of the light is same for all observer according to Einstein, right? And according to the measurements as well. What happens is now, if delta x is larger, delta x prime is larger, delta t prime has to be larger as well. Okay, so the time measured by one person versus another person in different frame of reference, they are not same. So time are not same. So time measured by this observer at rest has to be larger. So larger, longer time means we say, okay, it's a dilated time. Okay. So now how do we figure out how much difference in time one measures? Okay. And we can do that just using the same idea and using simple geometry, Pythagorean theorem. Okay. And that's what this is. So in this experiment, what's happening is there is a meter. So yes, I try to draw, and when I try to draw everything, it kind of became a little bit mess. But let's suppose there is a meter here on the top of this car, and there is a meter over here, right? So what happens? Light emits, and for the person who is on this car right there, I'm saying that person is experimenter, the person who is doing the experiment, who is, letting the light get out here and go there and come back. So for this person, just like we saw the ball you throw from moving car, what happens? Ball goes straight up and comes straight down, right? So for this observer, what happens? So experimenter, what I'm saying here, for this experimenter, if this height or the distance between the clock is h, and speed of the light is c, which is the case, then what we can say is the time taken by this light to go over there and come back is equal to what? Total distance divided by speed, right? Remember, speed is distance divided by time. So if you are solving for time, it is distance divided by speed. So in this case, speed is speed of light, and total distance, since it went up and came down, I'm saying this is the one-way distance, okay? Separation distance between these meters, so light has to travel, go up and come down. So that's why this time measured by this observer over here or experimenter over here in this frame that is moving here, okay, is this. So now what we want to do is, what happens to this person, right? So remember, the ball was like going in a parabolic path for, in that when you throw the ball. So it's kind of similar. So in this case, what happens is the light not going to just come back. It has to hit the mirror and gets reflected. So it reflects following the law of reflection for this observer here. Okay. So for this observer, clock is moving, right? And for the experimenter or the observer inside here, the clock is not moving. It's same place, just like you are sitting on the car and there is book or bag next to you on the car, and car is moving. So since you, car, and bag all are moving, so relative to each other, you and bag, they are not moving. So that's why the bag arrives to your home as you arrive to home. Okay. But if the person is outside, let's say this person is still on campus, then what happens? Bag started here and then arrived here. In that in that process, this not being the bag, it's light that's going up and down, it followed this path. So we can make a triangle out of this, okay, right triangle. So for example, what happened? Let's say halfway. So light starts from here and goes all the way there, detected. So if we look at the halfway, what happens? See, the light traveled, how much distance here? Speed times time interval, but since we are saying, okay, the time interval, uh, we are just looking at halfway here, so we are saying delta t over 2 there, okay? And similarly, since the train is moving with speed v, so distance traveled by train in time interval delta t is v times delta t, but we are not looking for this whole distance, rather just halfway, so that we can make nice triangle. So the length of this triangle is this much here, V delta t over 2. And for this one, C delta t over 2. And these delta t are the time measured by this observer here. Okay. So this delta t 0 is the time observed by the experimenter already inside that moving train where clock is not moving. And this delta t is the time given by a clock that is moving for this observer. Okay, so notice the difference between those two times. So that's why the notation is different. Here there is delta t 0. Over here this is delta t. Okay, so now we have a nice triangle, and from Pythagorean theorem we know this is this square, for example h square plus this square must be equal to this square. Hypotenuse square is equal to the sum of the other two sides squared, right? So we can do that. And by the way, I'm just rearranging this for h first before I write that. So now this is for this triangle over there. Just like I said, h is squared plus this thing is squared. So the b has to be squared, delta t has to be squared, 2 has to be squared, so it becomes 4, and so on. So over here, it is the speed of light because light is moving here. So that's why c over there. Over here, this is speed of the train. So that's why this is v. Okay, so that's the difference over there. Otherwise, the time is same. So now what we can do is we want to compare, like how this time delta t is 0 and delta t are related. That's what we want to know. So what we can do is we can replace this h square, since this height is same for both of them, both observer. Okay. What happens is we can replace this h by this c delta t 0 over 2. And since it is h squared, we have to square this one. So that means we're going to have these things squared, and this is going to be 4 when we square the h. So let's write that down. Okay. So now what we have is delta t square in one side, delta t 0 square in one side, and delta t square on the other sides. So it looks like there is 4 here, 4 here, 4. So we can cancel that. So once we do that, we're going to have just those numbers on the top, right? So that's that. So here there being delta t 0 square, delta t 0 square, sorry, not 0, but just delta t and delta t. I factor that out. So I'm left with c square here and b square over there with negative sign. So that's what you see. Simply 4 was cancelled there. So now let's solve this one for delta t. So that means let's bring this to underneath this. Okay. And that's what I'm doing here. Okay. So we can rearrange this. So for example, let's say if I were to factor c squared from here, what's going to happen? This is going to be 1 minus b squared over c squared. If I were to factor, okay, c squared. So that's how it's going to look. So this c squared down here, and that's going to cancel. So that gives me just delta t 0 squared over 1 minus b squared over c squared. So that's the delta t squared. So delta t is going to be just this one here. Okay. So delta t 0 squared under the square root simply is delta t 0. But this 1 minus b squared over c squared has now square root in it. Okay. So now you see that there is a relationship between this delta t and delta t 0. So this quantity 1 over this is called gamma, called Lorentz factor. Oh, I think it's written there. Yep, that is called Lorentz factor. So what is this? This is the equation that gives you the difference between time measured by clock here or experimenter here and observer here, or the difference in time between two frame of reference that are moving with respect to each other with velocity v. Okay, so that is the time dilation equation. Okay, so we'll talk about more, talk about it a little more, but let's take a break first. Okay. Okay, folks, so welcome back. I just realized that my chat was closed when Zoom went offline due to the internet. And I noticed there was direct message that says for the previous question, shouldn't it be C then? And so I think we are talking about this question here. And yes, for this, the correct was C. And I think I talked about that. So I think the question came before I corrected it. Okay, let's go back where we were. Okay. So here is a problem that says, okay, you have a twin brother, flies with the speed of very close up to the speed of light in a newly built spaceship for 5 years. How much older you are here on the Earth? This is also called twin paradox. So since one person moves with respect to another person, the time they measure gonna be different. So by how much? Let's figure that out. So B here is that, and the c is speed of light here. So usually this number becomes, ugly. So that's why these numbers are written with respect to c in the multiplication of c, okay? And then time interval is 5 years. So why this time is delta t is 0? Why? And by the way, this time is measured by the brother who flies. So for that brother, clock was at rest, right? So clock and the brother, that brother, they are not moving. Since they are in same spaceship, there is no relative velocity. And that time is the proper time. Remember in this experiment, what did we see? The experimenter is in moving card, and that's the time we said what delta t is 0. Okay. So we call that proper time. Delta t 0 is proper time. So what is proper time? So solving this kind of problem could be tricky if we cannot say which one is proper time, okay? So what is proper time? Which one is proper time? The time measured by the clock that is at rest with respect to the whoever is doing the measurement, okay? So in this experiment, the experimenter was right there in this train, and this person was measuring this time, and we said, okay, that time is delta t 0. So that's why that is proper time, okay? So same thing here. The twin brother is moving, and he has a clock, and he looks at clock, and the clock says, okay, you have moved for 5 years. Okay, so whatever kind of clock that is, maybe clock with the calendar. Okay, and now you are left behind waiting for your brother to show up, twin brother to show up. And what happens? How old? How long you have to wait? Is that person gonna be coming back in 5 years? Turns out not. Okay, so that means we are saying, okay, what is the dilated time? So this is what we call dilated time. What is dilated time? See, you were measuring time and comparing time with the clock that's moving, okay? So this time we call dilated time. This time is always larger or longer. So since these two times are related by this Lorentz factor, it's a good idea to calculate Lorentz factor. And it's easier to calculate that way when we write or when the speed is given in terms of the speed of light, right? So for example, in this case, I can write V, as something like this. So what happens? The C being squared here cancels with this. So now I am simply left with that. So this number becomes smaller because we are subtracting from 1. And it becomes exactly 10. So this number is 0.1 turns out, okay? And this becomes 10. So that means dilated time is 10 times more than the proper time. So let's suppose your twin brother left when you were you both were at 20 years old. When twin brother comes back, your twin brother is only 25 years. But you are how many years? 50, 50 plus 20, 70 years. Ooh, that may look like your grandkid now, your brother. And I don't know if you have watched the Interstellar movie. Maybe I should show you part of the movie that I have posted in my YouTube channel. Okay, so that's that. So to solve this kind of problem, you need to know. So I get it, but cannot wrap my head around it. So yeah, that is kind of interesting, isn't it? So it's not about just clock, even your biological clock. Remember, we have a heartbeat, right? And it beats around 70 times or so every minute, right? Do you guys know that? Normal heart beats around 70, 60 per minute. So about once in a second. So now if you are, moving really fast, what happens? Now it is not, what happens? It takes a lot longer. How long? 10 times more. So it was beating once in a second. Now it takes 10 seconds to beat. So your aging process is also slowing down like that. So here is a question for you then. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we got C and D majority, but we also got B. and A. So longest interval, proper time is actually shorter rather than longer. Dilation means longer. So that's why this is kind of not. The interval measured in a reference frame in which the two events occur a maximum distance from each other. That is, how far they occur does not matter, okay? And so that is not. So as long as, for example, let's suppose one train is moving here in Denver 40 miles per hour. Another train is moving somewhere else in Newark, let's say, 40 miles per hour. See, they are moving 40 miles per hour. They have same speed, means their frame of reference is same, basically. Two things, if they are moving with the same speed, then their frame of reference is same, okay? So the interval measured in a reference frame in which the two events are simultaneous. So that sounds kind of reasonable, but let's look at the other one. The interval measured in a reference frame in which the event is taking place. This is better than that one there, okay? So here we don't know where the clock is. So I think this is the best response in this case. So measurement has to be done in the same frame of reference at which the event is taking place, or whatever is happening there, you are measuring right there, not from the another frame, okay? So this Lorentz factor, let's talk a little bit about that. So in the previous problem, we saw Lorentz factor was 10. When is Lorentz factor 10? When the speed was 0.995 c, right? So over here looks like, it is like so actually I plotted this in a graph. So what value is that? It's not marked, but could be 0.99, something like that, okay? So you see that is around 7 or 8. So what happens is this beta thingy, this Lorentz factor, which is this, and sometimes Lorentz factor is also written as a 1 over 1 minus beta square. B over C, you are denoting that by beta, okay, just for simplification. So we are plotting this gamma Lorentz factor with the beta here, which is scaled velocity. So this is B over C basically. So that means when B and C are equal, which is not possible, that's when it becomes 1. So that's why by the time this becomes 1, this becomes kind of infinity, very large, okay? So it rapidly increases after 0.8 or so. See, it goes exponential like that, okay? Up to 0.1, even 0.2, what happens? The value of gamma is very close to 1. So that means this gamma 1 means what happens? Remember, our delta t is gamma times delta t is 0. So when gamma is 1, then both of these times are same. So for our usual speed we experience in our daily life, even for the fastest experience, for example, when we are riding plane, what happens? Here, for example, I have written, plane when it is flying at top speed, these big planes, right? That's long distance plane. When they are moving in top speed, they are moving around 600, 700 miles per hour. So what's the value of Lorentz factor when they are moving something like that? So this, when we convert that in meter per second, this becomes 269 meter per second. And what's the value of Lorentz factor? Still one, isn't it? Like you have to go to how many, uh, let's say significant figure? Too many to count. We are often working within two or three. So for two or three significant, it's still one. So that's why, when your brother or father or mother or sister, uh, comes flying 14 hours or so, they are not younger than you. You don't experience that because the value, this gamma for this kind of speed is 1. So that means the time difference, yes, theoretically there is, but practically there is not. Okay. So what they did was they put a clock. So you cannot tell by just looking at person, one is older than the other or not for this much difference. But what they did was, oh, where is that? I think this is on this slide, some of the example. So I think that example, I should have put that in the first, would have been more relevant there. So they put a clock in a plane, atomic clock that can measure time up to a nanosecond or even, femtosecond. Pico is 10 to the power negative 12 second. Femto is 10 to the power negative 15 second. Okay. And then they look at whether they compare the time of that clock that went on the plane versus clock on the ground. And they found there is slight difference, change in time. Okay. Another example is this. So yes, we haven't talked about half-life. At the very last chapter, we'll talk about half-life. So what half-life means is, let's say we have some pile of number of, let's say in this case, it says elementary particle like electrons, right? Protons. Muon is a kind of elementary particle that does not interact much with the other charges. So let's suppose we have 16 of it, and somehow let's say it decays. It gets converted into another one. So by the time, whatever time it takes to get from 16 to 8 or become exactly half of it, we call that half life. Okay. So it is only about 1.5 microseconds for this particle. So micro means 10 to the power negative 6 second. Okay. 1 microsecond. So it should, like disappear or disintegrate very quickly. But what happens is that a lot of them kind of arrives to the earth. So here is number. So for example, when they are created, so it created by this cosmic particle when it hits the atmospheric particle. In that case, they generate. And based on, their half-life, they should, you know, be, let's say done by, couple of factor more time than that. So that means by the time they move, let's say 2 kilometers or so, they should be all gone. Okay. So that's what that mathematics is telling us, even when they are moving very close to the speed of light, right? But what happens is they are reaching to the earth, they are moving this 55 kilometer. So what that means, their time, that we are measuring is dilated time. Although they have real life time is 1.5, what happens? Because they are moving though so fast, the dilated time is 10 times more, for example. So it becomes 15 milliseconds half time. So they may survive up to 30, 45, or even 60 milliseconds. So by that time, they can travel that much distance and can be detected here on the Earth. Okay. So it looks like there is another direct question here. Is that why studies suggest people who travel a lot live longer, or is this purely due to the positive experience? I don't know that, okay? But definitely that one does not matter in terms of, like they don't have like, so that speed, the travel speed, our travel speed is not large enough to see the change in time. So that speed is not relativistic. For that to experience, you have to be moving really fast. Okay. How fast? Not plane fast, not rocket fast, light fast. So you have to be moving like at least half the speed of light. And how much is that? Remember, light can reach to the moon in a snap of a second. I mean, time. So that's how fast you have to travel to experience any difference in time. Okay? So that's why the example is for this. Otherwise, for person like us, when we travel in the plane, the difference, I thought I brought this. Okay. Yeah, there it is. Okay. So 200 nanoseconds in one flight. 200 nanosecond, and nano means 10 to the power negative 9. 200 means 10 to the power negative second 7. So to see the 1 second time difference, how many flight you have to go? Millions of earth round flight you have to go to see the time difference of 1 second. So if someone is surviving longer, it's definitely not because of this relativistic effect. Something, a difference, experience, I don't know. If you can live a stress-free life, you survive, you can survive longer. That's what, you know, some people say. I cannot tell that. I cannot say that. I don't have proof of that. But maybe yes, okay. Happier you live longer. I think that's what social studies shows, but not sure about it. Okay, I'm not quite sure about it. Okay, it's very hard to do social experiment in a controlled way and come up with that kind of observation. We may see 1 or 2% living longer who travels, other maybe dying sooner. I don't know. They may, you know, they may catch some sort of disease or something like that when they are traveling all over, right? We don't know. So anyway, what is correct is yes, there is some time difference, but that time difference is not notable until you go close to the light speed. So maximum we can go is plane or rocket, and even the rocket speed does not make much difference. Okay, not the noticeable difference. Okay, so that's that. So now here is a question for you. So I'll let you look at the situation and answer this question. So I'll give you 1 minute and 30 seconds. Excuse me. 30 more seconds. and 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly proper time we got, and there are some dilated time as well. And we even have a daylight saving time. Isn't that interesting? So clock is at rest, and this portion is moving, right? This rider, broom rider, is moving. Clock is at rest. So clock is not at rest at the frame of reference of this rider. See here, rider is moving, but clock is not moving. You see that? So for the rider, clock is moving. So when you are driving car, what happens? The poles, tree nearby the road, they appears to be moving backward, isn't it? It seems like they are going back with the same speed you are driving your car. So for the clock that is at rest, this rider is moving at speed v. For the rider, clock is moving in opposite direction at the same speed. So for rider, clock is moving, not at rest. So that means it is not a proper time. Rather, it is a dilated time. So both of these have to be in the same frame of reference for this to be proper time. So this is a dilated time, folks. So yes, it could be confusing. Okay. This observer, for this observer, so the time observed by the rider, not this observer here, right? So that's why it is dilated. If it was for this observer who is also at rest, clock is also at rest, means they are at same frame of reference. Okay. Maybe based on my drawing, it may look like this clock is attached to this broom. It is not. Okay. I said clock is at rest. What frame of reference? Maybe I should have written on ground frame of reference, right? It is on the wall or something like that. That's not moving. Maybe that may have caused a little bit problem. So anything you like to add or ask here, folks, about this question here? Identifying proper and dilated time is important to, you know, let's say do the calculation, right? Otherwise, we may end up getting exactly opposite answer. Okay, then let's move on. Here is another question. Now, how about the length, you think? Okay, this we haven't talked about it. You may have read about it. I'll let you pull on this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. Mostly C, it's shorter. So yes, length contracts. Okay. So here basically, I'm basically saying the same thing. Okay. So train is moving very fast past a station. So frame of reference of train is S prime. It is moving with speed v, which is very fast. And there is another frame of reference, let's say. Observer at the platform wants to measure the length of the train. To do this, they note when the front and back of the train pass by fixed points at the same time, right? So for that, there has to be some sort of reference. For example, let's say this person already knows how long, like approximate, I don't know, some sort of marker, okay? This person, whenever, looks at the train, this person is there and looks at the train and sees, okay, it is. Now let's say there is a wall with a lot of markings. Oh, so this angle is not that large as I'm drawing here. So does the marking and measures the length, okay, here. So train passes, looks at, okay, where was the front end, back end, and, let's say put that in the head and then measures the distance on the wall, okay. So that's going to be the length measured by the observer. That's what we're talking about, who is outside the train. And then there could be another person who is already in the train. So he or she has all the time they need. Okay. So they can go here and then use their tape measure and measure when they are right there, right? So they're going to measure a length here. And this person here has measured another length. Okay. So this person is in the same frame of reference where the measurement is taking place. So that's why the length measured by this person gonna be proper length. Okay, whoever the experimenter is or observer is over there, it's gonna be proper length. But if you are outside and measuring the length, then that's gonna be not the proper length. We call that contracted length. Why? Because it happens to be shorter. Okay. So proper length is denoted by L0, just like time, we denoted that by delta t0 for proper time. So for proper length, we do L0. So that means the length measured by the rider going to be speed and time. And then another length measured by the observer at rest going to be b times delta t. B is same for both because that's the relative velocity between them. And why this portion here is measuring proper time? Because clock is at rest outside, just like we said, okay? So now, if we were to compare these, what happens? B gonna cancel. So divide one by another one. And then what's gonna happen? This is gonna be BT0 divided by B delta T. And this B looks like yeah, B cancels and they're going to be ratio of the delta T, delta T and delta T0 and L0 and L. And we know delta T is gamma times delta T0. So if we make use of that to compare these two times here, and then we get this relationship. So that's why the proper length is now longer than this length. So that's why it is called contracted, because the gamma is always one or bigger. One, I mean, if it is not relativistic, it is one, right? If the speed is really small or zero ideally. Otherwise, gamma is slightly more than one or very large. So depending on how big the gamma is, the L gonna be smaller by same proportion. So that's what this equation is saying. So just like this equation related these two times, now this equation is relating the length measured by two observer. a different frame of reference that are moving with speed v. And if you are wondering where the speed is, see, the gamma is the speed. Gamma has the speed. Gamma is 1 over 1 b square over c square under the square root. Okay, so b is there, right there in the gamma. So gamma is always bigger than 1 for moving object. So that means L is always smaller than the proper length. So I don't know if, sometimes in the social media, you may see video where you may see, like something is moving and then they are appears to be really small, like width is very small. The length gets contracted. And by the way, change in length takes place only in the direction of motion, not other direction, okay? If it is perpendicular to the direction of motion, there is no change in length. But if there is some sort of incline, then yes. So for example, this is this, or this could be this. So this incline is equivalent to this length in that direction. So it's x component that goes through the L. If that is L, this is going to be Lx. So this one goes through the contraction. Okay, Lx goes through the further contraction if it is already inclined. But if something is, let's say standing tall and then moving in that direction, then this height does not change. Only the width changes. So for example, if you can run really fast, like a flash or something like that, okay, then your width gonna be smaller than your usual width of your body. Okay? So that's what this length contraction is saying. So I don't quite remember I put the problem of length contraction in the note or not. Oh, I put together that not that long ago, but I forgot. But here I did not bring a problem related to that. Okay. I think I may have put one problem related to length contraction. And here I like to talk about speed. How do you add them? So for example, we said at the beginning, right? So problem was like, okay, 1c plus 0.95c is not equal to 1.95c. Rather, it has to be just 1c or less than 1c. So that's what we want to see. That's what we want to get. So for that, remember we have this formula here. Now that formula has to be modified. Something like this. So this is not quite a Lorentz factor here. Okay. But kind of looks like it. See, b square over c square, the product of two velocities. But what I like is I like to write something like this, because object could be moving away from each other or towards each other. So for that, we need to take account of sign as well, okay? So rather than writing formula something like this is a standard formula usually people use, but I like to write something like this. And it is easy to remember. How? See here, we want this velocity of A with respect to C, okay? Velocity of object A with respect to C or observed by C, let's say. Then here there is this VAB and BBC. See here, this B was at the last here and B is at the first. So if you look at here, it looks like BAC. You see that? So that's the order it has to be. So for example, let's suppose I say BAE and I said, okay, one is VAB. Oh, that's not B. if I want to write VAE, velocity of A with respect to E, and let's say we have this measurement, something like this, velocity of B with respect to Earth plus velocity of Earth with respect to, oh, hold on, BAE we want, right? So I should be starting from A, okay? And then it's a B, and then it should be B, and then Earth. See here, A and Earth, they are A and E. It starts at it ends at that E. It starts at A, it ends at E. And the common thing that goes here, you can think of, okay, they get canceled. Let's say you can think of, I'm not saying they cancel, okay? Once you have this written properly, this is just a product of those two divided by c squared. 1 plus product of those two divided by c squared, okay? So that's how the velocity adds. So now let's add those two velocities. Which one are those? 1 plus 0.95, and both of them are c. And over here, 1 plus 1 times 0.95, and c becomes c square, and this c square. So this cancels. So what we have is, see here what we got? On the top we have 1.095, 1.95 in the numerator, and denominator we have the same thing. 1 and 1 times 0.95 is 0.95 plus 1 is just. So now both the numerator denominator, that means they cancel, leaving us just the c over here, okay? So that's why this is c. Even easier, you try adding, let's say, c plus c, c plus c, 1 plus c times c over c squared. How much is this? This is c. C plus c is c. That's the that's the kind of formula we need, and that's what this is doing, okay? Oh, it's already 52. So I had a clicker question. Maybe I'll pull on this one next time, okay? And then move on to next chapter. But that's how it works. And the famous equation you may have seen on the T-star, it is also the consequence of that. So for that, we have to go through the momentum and energy, which we are not doing in this class, okay? Okay, sorry, I kept you a couple minutes more. So I'll see you next class, folks.